operation capacity analysis of aqueous homogeneous reactor using MCNP and origin computer code. Outline of presentation. Objective. Introduction consists of production of molybdenum-99 in nuclear reactor, technetium-99m in the medical field, production molybdenum-99 in aqueous homogeneous reactor or AHR, and then the methods. AHR simulation in MCNP 4C and origin 2.2. The reactor operation to get maximum molybdenum-99 product, and then the result, conclusion, and future work. Objective. The first is simulate the production and capacity analysis of molybdenum-99 in a novel aqueous homogeneous reactor using MCNP and origin computer code. The second, optimize the production of molybdenum-99 by varying the reactor operation time. Introduction. Radioisotope production is done in commercial reactor, and most of the detail of such production lies in the classified domain. Extensive research has been done to get the information about such reactor design, and a novel reactor is being proposed for the production of molybdenum-99. Molybdenum-99 production in current operating reactor. Molybdenum-99 is produced by fission, product, and activation, neutron activation. It will be decayed to be technetium-99m, and it decay again to be technetium-99 and decay again. Molybdenum-99 is produced by irradiating target uranium-235 in the reactor core. Molybdenum-99 is mostly result of uranium-235 target fission reaction with a fission yield about 6.1%. The fuel will be spent fuel as highly radioactive waste. Technetium-99m in medical field. Technetium-99m is produced from molybdenum-99 decay. It is used in millions of medical diagnostic procedures annually, like bone or brain scans. Technetium-99 emit gamma 141 kV with half-life 6.007 hours. This is the decay scheme. Molybdenum-99 is decayed to technetium-99m and decay again to be technetium-99. This is the energy of gamma that is used in the medical field. 141 kV gamma. Molybdenum-99 production in aqueous homogeneous reactor. In this reactor, all molybdenum-99 can be extracted from the liquid solution. Aqueous homogeneous reactor, or AHR, are a type of nuclear reactor in which soluble nuclear salt Example, uranium nitrate dissolved in water. Target and fuel become one liquid solution. There is no spent fuel. Simulate the nuclear reactor using computer code. MCNP4C computer code is used to analyze the criticality. Criticality means controlling sustained fission chain reaction by controlling neutron population in the reactor. Origin 2.2 computer code is used to calculate fission product, neutron activation, decay as a function of time, power, and fuel. This is the MCNP Visual Editor. Methods: developed a web page tool interface for Origin and MCNP. Used MCNP by optimizing fuel dimension to reach critical stage of the reactor. Use Origin by optimizing fuel, time, power to maximize the production of molybdenum-99 and learn about fuel consumption. This is the web page tool to make MCNP input. And this is the web page tool to make Origin input. MCNP is used for critical calculation. The input is geometry, material, atom density of the fuel, reactor vessel, and reflector. Origin is used for calculation, fission product, neutron activation, and decay. The input is fuel material in mole, reactor power, and then the time of reactor operation, and the time of shutdown. This is the flowchart. We start the program, start this analysis. We make MCNP input material, that is uranium solution geometry, and then we run the MCNP input. From the output we know is it supercritical or not. If the reactor is not supercritical, we increase the volume of uranium solution until it becomes supercritical. We use the data to make Origin input material, uranium solution, and then power and time. From the Origin output, we will take the molybdenum-99 as the result right here, and we return the rest of the extraction, the non-molybdenum-99 nuclide, to the reactor core, and this cycle is go and go, and for this research I make 10 cycle, and this the result, and this the finish of the flowchart. This is the reactor design. Right here is control root, and then uranium liquid solution input, reactor vessel, uranium liquid solution right here, This is the cooling coil. This is the reflector, and this is the place for uranium liquid solution drain. The design parameter of this reactor, the parameter, the value, reactor type aqueous homogeneous reactor, reactor power 200 kilowatt thermal, uranium 235 enrichment 19.75 weight percent, fuel concentration 250 gram uranium per liter, chemical form is uranyl nitrate, core temperature slightly below atmosphere, core height 122 centimeter, core diameter inside is 56 centimeter, reactor vessel is stainless steel, vessel thickness is 3 centimeter, the reflector is beryllium radial, reflector thickness is 30 centimeter, number of control rod is 6, and control rod is P4C. The reactor simulation in MCNP. This is the design of the reactor. This is from the top. The important parameter. This is the fresh fuel for the first cycle. This is the isotope, and this is the atomic density. The reactor vessel stainless steel 3 or 4, the nuclei, and this is the atomic density. Molybdenum 99 extraction flow rates. The source is from patent in 1997 by Bablock and Wilcox Company. The flow rate of the extraction in liter per day. There is a minimum mass flow. This is the minimum mass flow, and this is the maximum mass flow. The result. One is criticality or K effective, and the second is reactor operating time. Number 3 is molybdenum 99 product. The result, criticality, fuel solution height versus K effective. We see in this graph, if the solution height is increased, we see the K effective is also increased. This is the reactor supercritical with K effective is 1.2 right here. The height of the solution is 45 centimeter. For 45 centimeter height of the reactor solution, we get the fuel volume is 110.7 liter. The reactor operation per cycle. For this analysis, we make the reactor operation time in day with 7 series, start from 1 day until 7 day, and the shutdown is 2 day. All of the series is 2 day. and then the total from here we get starting from 3 day until 9 day. The calculation of the form solution is this liter 110 for the maximum extraction flow mass flow 86.5 liter per day. If we divide this number, we get the extraction time is 1.282 days. For the minimum extraction flow mass flow, we get the time is 12.82 days, and then we choose 2 days as the extraction time. We put it right here. Today reactor shutdown. The reactor will be restarted after shutdown. Reactor must be supercritical during operation or simulation. The K effective equal to number neutron at a generation divided by number neutron in previous generation. There is one booklet that is very important for this. That is xenon 135. Xenon 135 has large neutron absorption cross-section. Absorption cross-section is probability of neutron absorption. Half-life of xenon 135 is 9.2 hours. This is the xenon 135. It's produced from fission and also from iodium 135 decay. It will be disappear by decay and neutron activation. Criticality and xenon 135 concentration. Reactor will shut down for 2 days. We have to make sure that the reactor not subcritical after shutdown when we restart the reactor. The xenon 135 concentration versus time after shutdown for 3 days reactor operation. We see right here, this is the shutdown point time. This is the concentration of xenon. This is the time. The xenon concentration is at the first is slightly increase, and it will be decrease and decrease. We see if we compare with the data of the K effective with the same timing after the shutdown. Right here is shutdown. If we start the reactor 2 days or 48 hours after shutdown, we see right here the K effective is supercritical. For the fuel consumption, we see right here, there is 7 series of kind of operation, 7 type of operation, 3-day cycle until 9-day cycle. We make all of the type of the operation in 10 cycle. We see right here, this is for a 3-day cycle fuel consumption. This is the uranium-235 concentration right here, and the right here is a 9-day cycle. We see 9-day cycle consume more fuel uranium because the ratio of operating time is the biggest. 7 days operating time per 9 days per cycle, and 3 days every cycle consume less fuel because the ratio of operating time is the smallest. 1 day operating time per 3 days per cycle. Criticality during reactor operation. This is the time. This is the K effective. For all of the cycle, type of cycle, we see the reactor supercritical at all reactor operating time. The resume of all data series in this table: reactor operating time 1 until 7 days, extraction time days, all is in 2 days, and total per cycle in days starting from 3 until 9. The total cycle is all of the type in 10 cycle. We see the total time that needed is 30 days for this type of operation until 90 days. The total molybdenum 99 product inquiry in this row, this column, and if we divide this number to this number, we'll get the average daily molybdenum 99 product inquiry. For a note, every patient need 10 millicurie until 30 millicurie of technetium 99M. The average daily molybdenum 99 product we see in the chart right here, starting from 3 days per cycle until 9 days. This is the chart. The average daily molybdenum 99 product inquiry is maximum at 5 days per cycle. This is the conclusion. The reactor is supercritical in all reactor operating cycle. Reactor fuel volume 100.7 liter. Extraction time is in 2 days. The maximum molybdenum 99 production was for the 5-day cycle. The future work is benchmark the result by using another computer code. This is for validation, and then benchmark the result with experiment in the laboratory, and then try to use another type of fuel, for example uranyl sulfate. Thank you very much for your attention.